Okay, so let's start the session. So, good evening, everyone. I am Harshit Agrawal, and welcome to the 11th live session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. So, I am a PMRF scholar from IIT Bombay, and I will be taking weekly sessions for the course till the course runs. Now, what are these sessions about? So these are doubt clearing and interaction session. They will be conducted weekly, every Tuesday from 6 p.m. to 8 p.m. till the course runs. And how do we interact in the class in the sessions? By answering to the questions that I will ask in the chat box, by posting your queries in the chat box, or by raising hand, unmuting, and asking your query. Apart from the class, you can always use the discussion forum of the course. You can post your questions there, the answer to which will be given either on the discussion forum itself or in the next live session. And through this session, you will be able to answer the graded assignments easily, and you will it will help you to further understand complex topics holistically. So I hope everyone are clear about what the session is about. Now, in today's session, we will first have a recap of the last live session that was for week 10 of this course, just a quick glance. Then we'll continue with the discussion of week 11 content of the course, in which we will first introduce the torsional movement, what it is, and then we'll talk where torsion comes into action. Then we'll see designing a RC element for torsional movement. Then we'll talk about equivalent bending moment and shear stress that occurs when torsion is also taken into account. And finally, we'll do a numerical on design of an RC element under torsional moment. And with all these, we'll conclude the session. So this will again be a short session, an hour long session. So I hope everyone will be able to understand the content properly. Okay, so in the last live session that was for week 10 of the course, we talked about design of reinforced concrete staircase. So first of all, we looked what is the role of staircase. So we say columns are the members which help us to lift the particular structure vertically, and beams are and slabs are the members which provide us the stability on each floor. So staircase similarly helps us to connect two floors of a building. Now, the design of which is also very critical in case of a full structure design. Okay, after introducing to the staircase and what why it is important, we talked about different basic components of staircase, in which we saw what is tread. So tread is the horizontal part of the staircase. Riser is the vertical part of the staircase. Flight, total number of steps between two landings. Okay, headroom, the distance between the top of the floor and the top of a riser. Going is this part. Okay, if we have a step like this, okay, so this part is my going, and this part is known as nosing. And landing is the rest space that we provide. Okay, so this is known as landing. So all understanding all this component is important when we are designing a staircase. Now, what are the different types of staircase? In this we saw circular staircase. Okay, two staircase and straight staircase. Okay, the most simplest form of staircase is the straight staircase, for which we saw how it is designed. So in case of design, we saw different steps of designing. Like first, we need to calculate the effective span of the staircase, which is done based on the distance between the supporting beams. Now after that, we will first calculate the depth of the slab that is there underneath. A trial depth of the slab that we will assume based on L by D ratio that is provided in IS 456. Once we know, take an assumption of trial depth of the slab, we will do the load calculation. So what are different kinds of load when we talk about staircase? There is dead load, there is finish load, and there is live load. So as per IS 875, for different types of building, we have different conditions of live load and dead load, but live load that we need to consider. Okay. And after this, after calculation of load, we can calculate the moment that is acting on the base slab. This is the base slab, the moment acting on the base slab. And for once we calculate the moment, we can calculate the tensile reinforcement that we need to provide. And once we provide the reinforcement, we can again check for the minimum reinforcement and the depth, whether the depth that we choose is right or not. How it is done? By assuming this is a one way slab and by checking the deflection. And once we have provided the main reinforcement, we can provide the side reinforcement. Okay, complementary reinforcement we can say. So this diagram shows how that load calculation is done, and we saw it in deep in the last session. So I hope everyone are clear with the discussion that we had in the last live session. Any doubts in that?
No, sir.
Okay, so we'll proceed ahead with the discussion of this week. Now, this week we will talk about torsional movement. So first of all, it is important to understand what is torsion. Okay, so torsion are the stresses that occur when a structural element such as beam or column experiences a twisting or a torsional load. So suppose this is my element somewhere. Now generally bending happens like this. Okay, when the movement is acting like this, torsion happens when movement is acting such that it is twisting the member, okay, along the length. There is a twist that is happening in the member, that is known as torsion. And due to torsion, there can be failure in the member, which is take that also needs to be taken into account, and that is what we are discussing today. Now, in case of live structures like buildings, how this torsional stresses come into action. So suppose this is my slab, okay, and this is my beam. This is my slab and this is my beam. Okay. Now suppose at slab some movement like this is happening. Now that movement for beam will be not the may not be the movement which is acting normally to the beam. Okay. So if I draw the front view of the beam, okay, and from the load that is acting on the top of the beam, some movement like this would be occurring in the beam for which we are designing. But the moment that the slab is generating will generate a moment like this on beam. Okay. Now this movement will produce twisting to the beam in addition to the movement that is actually acting on the beam. So in such cases, especially when we are talking about joints like slab beam, column beam, okay, in such cases we need to take into account this twisting which can occur due to the movement of the other element. Okay, try to visualize it like you have a plain horizontal slab, and if it is bending, how, in what direction the movement would be acting, and due to that movement how my beam will be bending. So this beam would be bending like this, but we have designed it for bending like this. Okay, so that's why in such cases torsions come into action. So these torsion stresses are the result of applied moments or torque that causes structural element to rotate about its longitudinal axis. So that is what we saw here. My structure element, this is my longitudinal axis. So along the longitudinal axis my structure element will try to rotate, and that is what we need to take into account when we are talking about elements which are like this, where interaction is happening between two different elements. Okay, now how this is taken into account, before moving to that we need to see what all different kinds of structural forces we have talked till now. Okay, so we talked about flexure, and we talked flexure where it can occur in staircase, it can occur in slabs, it can occur in beams, it can occur in footing also, it can occur. Okay, now shear also we talked. Shear we basically mainly occurs in beams and in staircase. Okay, in staircase generally we don't provide stirrups, but we can say beams, and in slabs mainly we design for steer. Okay, shear. Okay, for footings we don't design for shear, we provide reinforcement such that shear won't be an issue. Axial load we talked in columns, and finally we are talking about torsion which can occur at the interaction of all beams, slab and columns. Okay, so this is how we are completing this part, the structural force part. We started this the first time I introduced you this whole diagram was when we were talking about columns, and in that class only I said that finally also we'll look it at again, so that everyone are clear with different structural elements and different structural forces and how it is associated together. Okay, so try to make your own diagram like this so that you have a better understanding. Like in terms of again going through the course also, it will be easy. So suppose you want to revise what happens in beam, so you should know in beam flexure is happening, shear is happening, so you can recap how to design for that. In slab it is flexure is happening, shear is happening, so how we design. In column axial load is happening, how we design. In footing flexure is the issue, how we design. In staircase what is the issue and how we design. So this will help you to have a clear clarity about different elements and different forces acting on the member. And today we are talking about the torsional stress. Okay, now how we design for torsional stress? Do we provide some different kind of reinforcement or some different kind of structural element, different kind of element to the structure? So see, when we were talking about bending moment, what we did, we provide longitudinal reinforcement that will resist the bending. Okay, and how we provided those longitudinal reinforcement as per clause 38.1 of IS 456. Now this is like load and bending is occurring, so we define. Okay, so for this is the, if this is my maximum bending moment happening in the beam, how much reinforcement I need to provide. Then we move to shear. So in shear we provide transverse reinforcement or stirrups. So these stirrups were designed for shear stress acting on the member, and that we designed as per clause 40 of IS 456. Now when we are talking about torsional movement, we don't provide any different kind of stirrups or longitudinal reinforcement. The design, like here I've said, the design of torsional forces, torsional movement we should say. So design of torsional moment doesn't demand for any different kind of reinforcement. Okay, but it's an addition to the existing bending moment and shear force that is made when there is torsional movement. Okay, so when some torsional movement is also acting on a member, what we do, the mu that we calculated for bending moment is updated, okay, with torsional moment, and the shear vu that we calculated for design, it is also updated when the torsion is also acting. Okay, because when torsion is acting like this, both shear and banding needs to be redefined. Okay, and that we do by just giving addition to the both shear forces and bending moment. Now how this is done, so we will see one by one what is the equivalent shear stress when there is torsion and what is the equivalent bending moment when there is torsion. So first, what is the equivalent shear stress? Okay, so suppose this is my element, we say that shear is acting like this. Okay, now when there is torsion acting, what will happen? There will be more shear resistance that we need to provide. Okay, so how we provide that? So my shear stress will now have two components due to factor design load that is acting, that is the shear that we discussed earlier also. For a simply supported beam, it is WL by 2. Okay, when when the simply supported beam is uniformly loaded, my shear stress is given by WL by 2. Now due to torsion, as per clause 41.3.1 of IS 456, we define the additional shear stress due to torsion is given by 1.6 times tau u by b, where tau u is the torsional moment. Okay, and b is the width of the element. Okay, so more will be my width of the element, lower will be my torsional stress. So you can see from here also, if my bending is acting like this, the more is my width of the element, the less stress it will generate in the element. So that's why as my B increases, my torsional stress will decrease. Now once we know both these values, we can calculate the equivalent shear due to torsion. Okay. Now this is my shear stress that is acting on a element. So using from this, I will calculate tau v. Okay, tau v is nothing but v upon bd. Okay. Now if my tau v is less than tau c max we can obtain directly from IS 456 based on the grade of concrete. Okay. Then if my tau is uh, greater than tau c max, then we need to redesign the structure element. If my tau v is less than tau c max but greater than tau c again you can obtain from IS 456. Okay, then we provide design for shear reinforcement. And if my tau v is less than both tau c and tau c max, then we provide nominal reinforcement. So this is what we know. We have discussed these three things earlier also. Just a recap to that. So here my tau v is the shear stress acting due to equivalent shear, both due to the load that is acting on the element and due to the torsional moment. Okay, so this is how we define shear stress. We will see in the question how we design. Okay, now what is the equivalent bending moment when there is torsion? So when there is torsion, again bending moment will have two components. Okay, so like this is my beam, suppose, and some load is acting, so we provide moment here. Okay, now when there is torsion, then we need to again provide additional moments, maybe on the side or maybe on the top also. Okay, so these are some additional moments that come into account when there is bending. Okay, one clause may not be discussed till now in the lecture, so I will talk about that. If my total depth is greater than 750 mm, okay, this is an additional part. Okay, just remember this. If the total depth is greater than 750 mm, then what IS 456 says, we also need to provide some side reinforcement, minimum two rebars on the side reinforcement. Okay, so just go through the code once for this and you will find this clause. When the total depth is greater than 750 mm, then side face reinforcement is also needed. So this also may need to be provided when there's torsion. Okay, so due to factored design load, we can calculate mu. So this mu is for simply supported beam uniformly loaded. And due to torsion, as per clause 41.4.2 of IS 456, what that clause says, the moment due to torsion is given by this equation, which is Tu times 1 plus d by b upon 1.7. So they might have reached this factor 1.7 from design and trials, and d is the overall depth and b is the width of the section. So you can see when we were talking about shear, the additional shear was only dependent upon the depth width of the section. But when we are talking about the moment is depending upon both depth and the width of the section. Okay. And once we know the moment due to both design load and torsion, we can calculate the equivalent moment ME, which is nothing but MU plus MT. Okay, and based on this equivalent moment, we can provide the longitudinal reinforcement in the tensile side. Okay, but there is one more thing. What code says, this is my MT and this is my MU. So if my MT, the moment due to torsion is greater than moment due to design load, what code says, we need to provide compression reinforcement for MT minus MU. So if suppose my MT value is 500 and my MU is 400, so I need to provide moment like rebars on the compression side also, which can resist a moment of 100 kilonewton meter. Okay, why this is so? Because when torsion is acting, when twisting is happening, there is bending which can occur in both top and bottom direction. So if my MT is very if it is more than mu, then it is recommended that we need to provide some additional movement reinforcement here also. But even if my MT is less than mu, though code doesn't say to provide compression reinforcement, but in normal design practice what is done, we need to provide additional reinforcement in the compression side for the moment empty. So if my empty, suppose it becomes 100, okay, it is 100, then as per IS code we don't need to provide any reinforcement in the compression side. But for safety purpose on field, it is recommended that we need to provide a reinforcement that can sustain 100 kilonewton meter moment in the compression side also. So this is a general practice which is opted on field, and that you can also do. Okay, so that is what I have written here. Though IS code doesn't say this, but we should follow this practice. Okay. Now, once we know, okay, so this was all about bending, how we provide reinforcement. Now, how we provide transfer reinforcement then when there is torsion. So, as per our clause 41.4.3, looped close hoops enclosing corner reinforcement shall be provided having a cross section area of ASV given by this equation. So now you will be confused a little, like here we talked about equivalent stress, and using this also we can calculate the transfer reinforcement. Then why there is a separate equation that has been given in IS 456 for calculating the transfer reinforcement? So this is the case, like from equivalent stress, whatever reinforcement you are getting, it should be designed using this equation. That should be the minimum ASC that you need to provide. And when we are talking about torsion, this is the main equation that we need to follow for providing a suitable area of stirrups. Okay, so if we assume initially SV of say 200 mm or 300 mm, we know TU, we know FY, we know everything. We can calculate ASV that we need to provide. Okay, and what is here B1 and D1? So B1 and D1 is the spacing between the end reinforcement. That is very simple. You can
So,
understand from the diagram also. Any doubt to anyone?
sir, I have one doubt. So, transverse means horizontal.
What? This is longitudinal reinforcement. Transfers mean those stirrups that we are talking. So one is along the length of the member, one is across perpendicular to the length of the member. So you can see this is the front view, suppose, okay, of a beam or something. So this will be by a longitudinal reinforcement which will be running along the length of the beam, and this will be my transverse reinforcement, the stirrups that using which we enclose the main reinforcement. Clear? This is the cross sectional view, okay, and this is the side view. Suppose this is the length of my beam. Okay, so these are my longitudinal reinforcement which will resist the moment, and these reinforcement will be enclosed by stirrups, okay, which will resist the shear and will help us to hold this main reinforcement in position. Both are the purpose of transfer reinforcement. Are you clear with the doubt? Okay, so these are the three conditions that code defines when we are talking about torsion. Okay, now to better understand how this is applied and actually how it is taken into design consideration, we will see one numerical. Okay, so what this numerical says: determine the reinforcement required for a beam of width 400 mm and depth, effective depth of 700 mm, and subjected to factored bending moment of 200 kilonewton meter and factored torsional moment of 50 kilonewton meter. And the factored shear force is 100 kilonewton. Use M20 grade concrete and Fe415 grade steel. Okay, so just try to solve this question. Try to think how this question can be solved. You know the equations that govern the equivalent shear and equivalent moment. Try to do the calculation, and then I will tell. Okay, I will wait for 5 minutes and then I will tell.